Plants, the very foundation of life on Earth, require a delicate balance of nutrients to thrive. While nitrogen often steals the spotlight, phosphorus plays an equally vital, albeit less celebrated role. This often overlooked element is essential for a plant's very existence, driving fundamental processes that underpin growth, development, and reproduction. Imagine phosphorus as the energy currency of the plant kingdom. It forms the backbone of DNA, the molecule that carries the genetic blueprint of life. Without phosphorus, plants couldn't store or transfer genetic information, hindering their ability to grow and reproduce. Beyond genetics, phosphorus is a key component of ATP, adenosine triphosphate, the molecule that fuels countless cellular processes. From photosynthesis, the process by which plants convert sunlight into energy, to nutrient uptake and the transport of sugars, ATP powers it all. Phosphorus also plays a crucial role in root development, enabling plants to establish strong root systems that efficiently absorb water and nutrients from the soil. This is particularly important during the early stages of growth, when plants are most vulnerable to environmental stresses. The availability of phosphorus to plants is intricately linked to its journey through the soil. Unlike nitrogen, which exists abundantly in the atmosphere, phosphorus is primarily found in rocks and minerals. As these rocks weather and break down over time, they release phosphorus into the soil solution. However, this release is a slow and gradual process, making phosphorus a relatively immobile nutrient in the soil. Once in the soil solution, phosphorus can be absorbed by plant roots or become bound to soil particles, rendering it temporarily unavailable. Soil pH plays a pivotal role in phosphorus availability. In acidic soils, phosphorus readily binds to iron and aluminum oxides, forming insoluble compounds that plants struggle to access. In alkaline soils, phosphorus can react with calcium, forming equally inaccessible compounds. The ideal pH range for phosphorus availability varies depending on soil type, but generally falls between 6.0 and 7.0. Maintaining this delicate pH balance is crucial for ensuring plants have access to this essential nutrient. For millennia, the phosphorus cycle, the natural movement of phosphorus through the environment, remained relatively balanced. However, with the advent of modern agriculture and industrialization, human activities have significantly altered this delicate cycle. The large-scale production of phosphorus-rich fertilizers has dramatically increased the amount of this nutrient entering our ecosystems. While essential for feeding a growing population, the overuse and inefficient application of fertilizers can lead to a cascade of unintended consequences. Excess phosphorus not absorbed by plants can leach into waterways through runoff or infiltrate groundwater. This nutrient overload disrupts the natural equilibrium of aquatic ecosystems, fueling the excessive growth of algae and other aquatic plants. The phosphorus we use to fertilize our crops and gardens doesn't magically appear. It comes from phosphate rock, a finite, non-renewable resource primarily mined in a handful of countries. While estimates vary, some experts predict that easily accessible reserves could be depleted within the next century. This looming scarcity has profound implications for global food security. As phosphorus reserves dwindle and become more expensive to extract, the cost of food production is likely to rise, potentially impacting access to affordable and nutritious food, particularly in vulnerable communities. The geographic concentration of phosphate rock reserves also raises concerns about supply chain disruptions. Political instability, trade disputes, or natural disasters in key producing regions could significantly impact the global availability and price of this essential resource. Section 5. The consequences of excess. Eutrophication and beyond. The excessive influx of phosphorus into aquatic ecosystems, primarily from agricultural runoff and wastewater discharge, triggers a process known as eutrophication. While seemingly beneficial at first glance, this surge in nutrients leads to a cascade of negative impacts. As algae and other aquatic plants flourish, they form dense mats on the water's surface, blocking sunlight from reaching submerged plants. This disrupts photosynthesis, the very foundation of the aquatic food web, and leads to oxygen depletion as these organisms die and decompose. The resulting low oxygen levels, known as hypoxia, create dead zones where fish and other aquatic life cannot survive. These dead zones are becoming increasingly common in coastal areas and freshwater ecosystems worldwide, jeopardizing biodiversity and the livelihoods of those who depend on healthy waterways. Section 6. the importance of responsible stewardship. Given the finite nature of phosphorus and its potential to disrupt ecosystems, responsible stewardship of this essential nutrient is paramount. We must shift from a linear, wasteful approach to a circular one that prioritizes conservation, reuse, and recycling. This requires a multifaceted approach, encompassing changes in agricultural practices, wastewater treatment technologies, and consumer behavior. By working together, we can ensure that phosphorus is used efficiently and sustainably, both for the sake of our environment and future generations. Section 7. Precision Agriculture Tailoring Phosphorus Applications. One promising avenue for optimizing phosphorus use in agriculture is precision agriculture. This technology-driven approach utilizes sensors, GPS mapping, and data analysis to tailor fertilizer applications to the specific needs of each field and even individual plants. By precisely matching phosphorus applications to crop requirements and soil conditions, farmers can significantly reduce fertilizer inputs without sacrificing yield. This not only minimizes environmental impacts, but also improves farm profitability by reducing input costs. Section 8. Organic Practices, Harnessing Nature's Phosphorus Cycle. Organic farming practices offer a holistic approach to phosphorus management that focuses on building soil health and harnessing the power of natural cycles. By minimizing soil disturbance, incorporating cover crops, and utilizing compost and manure, organic farmers foster a thriving soil ecosystem that enhances nutrient cycling. Cover crops, planted during fallow periods, play a crucial role in phosphorus retention. These plants take up excess phosphorus from the soil, preventing it from leaching into waterways. When the cover crops are incorporated back into the soil, they decompose, releasing phosphorus gradually, making it available to subsequent crops. Section 9. Phosphorus, Reclamation, Closing the Loop. As we strive for a more circular economy, recovering phosphorus from waste streams is essential. Wastewater treatment plants, once viewed solely as sanitation facilities, are now being recognized as potential sources of valuable resources, including phosphorus. Advanced technologies are being developed to extract phosphorus from wastewater and sewage sludge, transforming these waste products into valuable fertilizers. By closing the loop on phosphorus use, we can reduce our reliance on finite mined resources and minimize environmental impacts. Section 10. The future of phosphorus. A shared responsibility. The future of phosphorus is intertwined with the choices we make today. It's a shared responsibility that requires collaboration among policymakers, scientists, farmers, industry leaders, and consumers alike. Governments play a crucial role in implementing policies that promote responsible phosphorus management, such as incentivizing sustainable farming practices and investing in phosphorus recovery technologies. Researchers continue to explore innovative solutions, from developing phosphorus-efficient crops to creating alternative fertilizers from renewable sources. Section 11. A call to action, preserving phosphorus for generations. Preserving phosphorus for future generations is not just an environmental imperative, it's crucial for global food security and economic stability. By embracing sustainable practices, investing in innovation, and promoting responsible consumption, we can ensure that this essential element continues to nourish life on Earth for generations to come.